Hello everyone, welcome to my channel. To those who are new in this channel, I am Engineer J. I am a civil engineer and I am also currently teaching as an engineering professor. And in this video, we will continue our discussion on conjugate beam method. So this is the third part of our discussion on conjugate beam method. And if you have never watched my the last two parts of this discussion, I have posted the link of the part 1 and part 2 in the description below. So please watch all of my videos regarding conjugate beam method. And we have this example number 3. So in example number 3, we are asked to determine the deflection at point C. So this is the beam. We have 3 external supports and we have 1 internal support. So we have 2 concentrated load at point B and point F. So basically, all you need to do here is, of course, compute the reactions using equilibrium equation and draw the shear and moment diagram. But to expedite the process, so I have already drawn the moment diagram here. So this is our moment diagram. So at point B, we have 270. At point T, we have negative 270. And at point E, we have negative 202.5. So you can draw the shear and moment diagram. And if you do not know how to draw the moment diagram, so I have separate videos for that. Now, take note, as what you can see, we have 2 different moment of inertia. We have moment of inertia on member AC, which is 2080 times 10 raised to the 6, that is in millimeter to the 4th. We also have moment of inertia C to F, which is 1040 times 10 raised to the 6 millimeter to the 4th. Okay? But since we have 2 different moment of inertia, we need to make this beam uniform in terms of shape. So how are we going to do that? So we need to choose which of these 2 moment of inertias we will make as our reference moment of inertia. So we need to get which is our reference moment of inertia. So I would choose ICF here as our reference. So we have reference I is equal to our moment of inertia CF. Okay? So you can also use IAC as your reference. Now, as what you can see here, the relationship of the moment of inertia of CF and moment of inertia of AC can be expressed as the moment of inertia of A to C is basically twice of the moment of inertia of CF. Correct? Since if you multiplied it by 2, you would get 2080. So therefore, you can say then that our moment of inertia of member A to C, A is basically equal to twice of the reference moment of inertia. So therefore, we can say that member A to C is twice the reference moment of inertia, and C to F is the reference of moment of inertia itself. Okay? So therefore, we have 2I and I. Again, we set ICF here as our I. Okay? Now, in our moment diagram, since we have different moment of inertia, we can set the moment at point B is equal to 270 over twice the flexural rigidity, since we are adapting 2I here. Okay, since we have moment of inertia 2I, and I again here is the moment of inertia of member CF. And in point D, basically this is just EI, since this is on the reference beam or reference moment of inertia, and our DE here, or our moment of inertia at point E, is negative 202.5 over EI. Again, this is EI since ICF is our reference moment of inertia. And our point B here is on member AC. Again, our AC, the moment of inertia, is twice of that ICF. Thus, we have 2 times the flexural rigidity on the denominator. So therefore, we have to make this beam in uniform cross-section by dividing 270 here by 2. So therefore, we would have 270 divided by 2. We would have 135 over EI. And the rest of the moments will stay the same. Okay? So therefore, we have now our moment diagram after we apply moment of inertia. So this should be our moment diagram, let's say moment diagram 2, and this one is our moment diagram 1. So this would be our new moment diagram. Now again, we need to convert everything to conjugate beam. Okay, so we need to convert the supports into conjugate beam equivalent support, and we have a new load, and we all know that the new load in our conjugate beam is the moment diagram itself. So we will be adapting this moment diagram as our load diagram for our conjugate beam. So we have this as our conjugate beam. So in conjugate beam, again, we adapted the moment diagram as the load diagram, and the direction of our load, since we have positive moment from A to C, that means we have a load which is acting upwards. Okay, and for C to F, we have negative moment, so therefore all the loads there is acting downwards. So this now our conjugate beam, and next thing is that we have to change all the support. So at point A, we have hinged in the real beam, so therefore point A should remain as hinge. Point C is internal hinged, so therefore that would become as interior ruler. Okay, since if you do not know, I have explained to you why these supports changed to different support when we are converting conjugate beam. So this one is C, okay, this one is our A, B, and D here is an interior ruler. That means that would change as a internal hinge. So therefore, we have internal hinge here at point D. Now, point E is an interior ruler. That means we have to change that into internal hinge, and thus we have internal hinge at point E. So again, this is an internal hinge, and this is internal hinge as well. Now, we have a free end at F, so that means that should be converted into fixed end support. Okay, so at point F, we have here fixed end. Okay, so we have now our conjugate beam. The lengths are still the same. We have 6 meters from A to C, and A to B is 3 meters, and B to C is 3 meters as well. C to D is 3 meters, D to E is 5 meters, and E to F is 3 meters. Now, our goal here is to determine the deflection at point C. So that means we will be computing the internal moment at C. So again, since deflection is equivalent to moment at that specific point. So again, you can use either shear and moment diagram, or you can use moment equation, but to expedite the process, I will be using here the moment equation. Since we will be cutting at point C at this point, or that is 6 meters from A, so we have to compute the reaction at A at least. Okay, so we can assume that our A here is going downward. We have here AY. So we have to compute the value of AY, but take note, we have to compute first if this one is determinate or indeterminate. So we have to compute the number of reactions. So we have 2 here, we have 1 reaction, we have a 2 at the internal hinges, and we have 3 at the fixed support. Now take note, at the fixed support, we do not have a force acting horizontally. So therefore, we can say that our horizontal force at point F is equal to 0. So therefore, this should be the only reaction that we have at point F is 2. So therefore, we have 9 reactions. Then we have 3 times the number of rigid member here is 3. Therefore, we have 9 equals to 9. That means this one can be computed using the process for determinate. So again, we need to compute the value of AY. so that we could isolate this triangle, and that we can solve the internal moment at point C. But how are we going to compute AY? So since we have three supports or three exterior supports, so we can't directly solve AY here by not applying simultaneous equation. So in this case, I'd like to sum up moment at D. So we cut at point D, and then after that we cut at point E, then sum up moment again, so that we would have two variables here. We have AY, and we also have the reaction at CY, and then we apply simultaneous equation. So we cut at internal hinge D, so we would have this one. So at point D, since this one is internal hinge, so we would have, let's say we have force vertical dy and force horizontal dx. So we can sum up moment at D, and this equals to 0, counterclockwise positive. So we have AY times 9, okay, plus CY times 3, minus the load, the resultant of this triangle. So we can just include all the triangle. So we have 1/2 times 135 times 6, and the resultant is at midpoint, since this one is a symmetrical triangle. So that would give us the moment arm from D. We have a 6. Then we add the moment due to this load. We have 1/2 of 3 times 270, then the moment arm times 1/3 of 3. Now take note, this positive because this load here generates counterclockwise moment with respect to D. Okay, and this equals to 0. So we have 9AY plus 3CY. This is equal to 2025. So this is our first equation. Since again we have two variables, AY and CY, we need to add additional equation so that we can perform a simultaneous equation into this one. So where are we going to get the second equation? So we just need to cut at point E, or the location of our internal hinge. Okay, so we cut at point E. Okay, so we would have this free body diagram. So we can sum up moment at E is equal to 0, counterclockwise positive. So we have here AY times the moment arm from E is 14, correct? That is from E. And we have CY plus CY times the moment arm from E is 8, correct? Minus the load, so we have 1/2 of 135 times 6 times the moment arm from E is 11. Then we add this triangle here. Since this rotate counterclockwise with respect to E, that means we have 1/2 times 3 times 270. Now the moment arm from E is 5 plus 1/3 of 3. That's the location of the resultant. Plus, now take note, this one is trapezoid, so it might be difficult for us to compute the centroid or the moment arm. So we divide it into triangle and rectangle. So let's begin with the rectangle. We have 202.5 times 5 times 2.5. That's the moment arm. Plus, now for the triangle, we have 270 minus 202.5, this height here. Then we have to multiply it by 1/2 since that is triangle, times the length 5, and the moment arm is 2/3 of 5. Okay, and this equals to 0. In equation, we have 14AY plus 8CY, and this equals to negative 1068.75. And this one is our second equation. So we have now two equations. 9AY plus 3CY is equal to 2025. And 14ay plus 8cy is equal to negative 1068.75. So we will now be solving for the value of our ay and cy. Now you can use either substitution method or by elimination method to this one. So you need to apply your knowledge in algebra. So by using your calculator, actually you can get ay here is equal to 646.875, and the unit would be in kilonewton square meter. Okay? And our cy here is equals to negative 1265.625 kilonewton square meter as well. Okay? So we have now the reaction at ay and the reaction at cy. So we have ay is equal to 646.875 and cy is negative 1265.625. Okay? So again, since we are asked to compute the deflection at point C, then we should compute the moment at C. So in that case, we can cut at C. Okay, we cut at C. We would have this free body diagram. We assume that our moment here is in clockwise direction. So we assume that is negative moment. Okay, so that is our moment C. And we have shear. Basically, the shear here is equal. We have shear here just to the left of C. Okay, so we have 130 kilonewton. And we have 135 kilonewton meter load here. So the distance is 6 meters. And then we can sum up moment at C is equal to 0, counterclockwise positive. So we have 646.875, then times 6. Then we have minus 1/2 of 135. So we set that as one triangle since this is symmetrical. So we have times 6, and the moment arm is 3. Okay, and of course, we have the moment. We have minus moment C is equal to 0. So we have our moment at C. The internal moment at C here is equal to 2666.25. So this is now the moment at point C, which is basically our deformation or deflection at C. So therefore, the deflection at C is 2666.25 over EI. Okay? And since we have positive moment here, therefore, our assumption that moment C rotates clockwise is correct. So that means we have a negative moment or negative bending since this generates a frowning curvature. That means we have a deflection here, which is we have downward deflection. And since we need to compute the exact deformation, then we need to substitute the value of E and I. Now we know that our E here is equal to 200 gigapascal, and our reference moment of inertia I is equal to ICF, which is this one is 1040 times 10 raised to 6 millimeter to the fourth. This is our moment of inertia, or the reference moment of inertia based on our computation in the beginning of this problem. Okay, so we have here deformation C is equal to 2666.25. Now we need to convert kilonewton cubic meter into Newton cubic millimeter, so we multiply it by 1000 raised to the fourth so that we would have Newton millimeter cube. Over E, we have a 200 times 10 raised to the 3. This is in Newton millimeter squared, times I here is 1040 times 10 raised to the 6 millimeter to the fourth. We can cancel out Newton millimeter squared, and the remaining here would be millimeter squared. But we have cubic millimeter in the numerator, so we can cancel out millimeter squared. So the remaining unit would be in terms of millimeter. And the answer here would be 12.81 millimeter. So this is now the deflection at point C. Okay, and that ends this discussion on conjugate beam method. Thank you guys for listening, but please don't forget to subscribe to my channel for more videos. Have a great day. God bless and thank you.